I usually wait until the class period's done to start trying. So we're in section 2.2, and we're going to be talking about logic. Now let me give you just a little background, a little motivation of why we're talking about logic now. Logic really has to do with how information, how knowledge is, how facts are structured. And so we want to learn some rules about how they're structured and how we can make arguments, how we know what we know. The reason we're doing it now is I mentioned right at the beginning of chapter 1 about Euclid and how he wrote this big set of books called The Elements, all about logic, or all about geometry. Well, Euclid was really the first person that used logic in a systematic way, in an organized way, to put together information about math. So that's one reason that we're studying it now, is because Euclid was really important in the history of using logic, and he used logic to come up with the system of geometry. So we're kind of following along with what Euclid did. The other reason that we're talking about logic now is logic is really the building blocks of everything that we do in math. Math is all based on logic, all based on the types of information, the types of arguments that we're going to talk about during chapter 2, the type of thing we did for the opener. All of math is built on that kind of information. So logic is really one of the very basic building blocks of math. So that's why we're doing it now. And it seems like there's a lot of words and we do a lot of talking, but really the way we know things, the way we figure out things in math is using these kinds of tools. So let's start out with an easy example. Can we all agree that all Camaros are Chevrolets? So if a car is a Camaro, then it is a Chevrolet. We can all agree on that? All right. I'm going to put that information into a diagram. We call this kind of diagram a Venn diagram or an Euler diagram. Euler is one of the most famous mathematicians ever, so that's why they're named Euler diagrams. So I'm going to make a Venn diagram or an Euler diagram about Chevys and Camaros. So here's my big category. This big rectangle represents all Chevys. Well, inside that big category, and it doesn't matter what shape I make these, I can make it squares or circles or rectangles. Inside there is Camaros. So this Venn diagram or Euler diagram is telling us if a car is a Camaro, then it is a Chevy. The diagram and this sentence mean exactly the same thing. My Camaro is inside the bigger category of Chevy. So if our car is in here, if it's a Camaro, we know it's also in the bigger set. We know it's also a Chevy. So our diagram and our sentence mean the same thing. Now we call this kind of sentence, where we have an if and a then, we call that a conditional statement. So I'm just going to say if, then is a conditional statement. So our opener, if you are a math teacher, then you know algebra, that's a conditional statement. Sometimes we shorten it and we just call them a conditional. But a conditional statement or a conditional means we write something with an if and a then. If we're going to use symbols, we would say if P, then Q. Where P is something and Q is some other thing. So for our opener, P would be you are a math teacher. And Q would be you know algebra. And we would write if you are a math teacher, then you know algebra. In this statement, P is a car is a Camaro. If a car is a Camaro, and Q is it is a Chevy. So P and Q just mean some kind of some part of our statement. We can also write this double arrow, and we read this P implies Q. All of these mean the same thing. If P, then Q, P implies Q. And these are all ways of writing these conditional statements or conditionals. Now the P part and the Q part, we give them names. The part after if and before then is called the hypothesis. So this is our hypothesis. Our, what's that? And the part after then is called the conclusion. And when we're looking at our hypothesis and our conclusion, they do not include the word if and they do not include the word then. So on this example up here, our hypothesis is a car is a Camaro. That would be our hypothesis for this conditional statement. Our conclusion is it is a Chevy. For our opener, if you are a math teacher, then you know algebra. A hypothesis, what would the hypothesis of that one be? That's the whole thing. So what's the hypothesis? The hypothesis is after if and before then. You are a math teacher. So the hypothesis would be you are a math teacher. What would be the conclusion? You know algebra. So you don't include if, you don't include the then. It's just the parts in between. So our hypothesis for our opener would be you are a math teacher. Our conclusion is you know algebra. So the part after the if and before the then is called the hypothesis. The part after then is called the conclusion. So we have our conditional statement that has an if and a then. We can use a Venn diagram and our Euler diagram to show our conditional statement. And we know what our hypothesis and our conclusion are. So from our Venn diagram, the hypothesis is going to come from the inside part. If a car is a Camaro, then it is a Chevy. So our conclusion comes from the outside, from the bigger part. All right, any questions on that so far? Okay. Let's say we know that Joe owns a Camaro. So we already know the Camaros are Chevys. We have a Venn diagram or an Euler diagram for that. So let's draw an Euler diagram that shows that Joe owns a Camaro. So here's my here's my diagram, and it doesn't have to be a rectangle, it can be any shape. So we know that we have Chevys, our Camaros are Chevys. So here's my category for Camaro, and here's Joe's car. Joe has one car in the set of Camaros. From this Euler diagram, or this Venn diagram, we can make what we call a logical argument. So I'm going to write, we know that if a car is a Camaro, then it is a Chevy. We know that Joe owns a Camaro. So what else do we know about Joe's car? Joe's car is a Chevy. So what we have here is a logical argument. It's what we call a logical argument. We put together the things that we know, and we figured out then what has to be true if we know those things are true. This is exactly what we did on the college trip project. If we want to visit a college on Monday, then we have to fly to Arizona. Once we're in Arizona, if we want to get to another meeting, then we have to fly someplace on Tuesday and not go to a meeting. And we put together all of these things that had to be true until we finally had our schedule. So what we were doing on the college trip project is making a logical argument based on the information that we had from our meetings and from our flights and from our schools. So this is exactly what we were doing in the college trip project, is putting together an argument like this. We just didn't do it in quite as formal of a way, but that's exactly what we were doing. And what we say is, and this is why we use it in math, is that our conclusion is logically certain. It has to be true. There's no other way that it could happen. And that's exactly what we did with our college trip. In order to visit our 7 colleges, things had to be one specific way. And arguing this way, if we're starting with what we know is true and going step by step for all of the things that we know is true, this is called using deductive reason. So all of this is deductive reasoning. Starting from things that we know are true and linking them together is called deductive reasoning. This? That's a DE. And this, if you ever read Sherlock Holmes, you ever watch any Sherlock Holmes, they have a bunch of new Sherlock Holmes shows on television. Sherlock Holmes uses deductive reasoning. This is true, that means this is true, that means this is true, so this is how things had to happen. All right, questions on making logical arguments, linking things together, making logical arguments. All right, let's talk about reversing conditionals. We did a little bit of this with the opener. So if we reverse our conditionals, if we switch the hypothesis and the conclusion, so we change the order, so if we have a conditional and we change the order, we switch the hypothesis and the conclusion, we get what we call the converse. So we switch the order, we get the converse. So let's go back to our example about the car. We said that if a car is a Camaro, then it is a Chevy. Let's make the converse. So how are we going to write the converse? What do you think, Preston?
If the car is a Chevy, then...
If a car is a Chevy, then it is a Camaro. So this would be my converse. Is this true? No. So when we make our converse, the converse is not always true. If our original conditional is true, the converse is not always true. So that's where we're going next. So hold on to that thought. So when we make our converse, it's not always true. When the converse is true, we get something that's kind of special, and we'll talk about those later. But our converse is not always true. I'll do this. Now, Lindsay gave us an example of a car that is a Chevy that's not a Camaro. So a Silverado is not a Camaro, but it is a Chevy. An example that shows that a conditional is false, something that shows that a conditional is false, is called a counterexample. So for our example, a Silverado is a counterexample that shows that this converse is not true. A Silverado is a counterexample. A Volt would be a counterexample. Any car that's a Chevy that's not a Camaro would be a counterexample. It shows that if a car is a Chevy, then it is a Camaro is not true. What about for our opener? If you are a math teacher, then you know algebra. Let's make the converse of that. If you know algebra, then you are a math teacher. We talked about that already. We said that's not necessarily true. So what would be our counterexample for that one? This entire class would be a counterexample for that. You guys know algebra, but you're not math teachers. So anything that shows that a conditional is not true is called a counterexample. Let me talk about, let's do a couple of other examples where a conditional is true and a converse is false. Let's say if I have $20, then I have cash. Is that true? If I have a $20 bill. If I have a $20 bill, then I have cash. Is that true? Okay, let's turn it around and make the converse. If I have cash, then I have a $20 bill. Is that true? No? I could have a $1 bill. I could have any other kind of money. I could have a penny in my pocket and still have cash. Let me think of another one. If you are in geometry, then you are studying math. Is that true? Yeah? Let's make the converse. If you are studying math, then you are in geometry. Is that true? No? What would be a counterexample? Algebra 1. If you're in Algebra 1, you're studying math, so you're not in geometry. So those would be examples where the conditional, our first statement is true, the converse is not true, and we came up with counterexamples. All right, one last thing to talk about, and then we'll be done. Logical chains. And this is just another way of making a logical argument. So I'm going to put up three statements, and we want to link them together to make an argument. So my first one: if there is a parade, then we have fireworks. My second statement is, if it's 4th of July, I'm going to say July 4th, then flags are flying. And my third statement is, if flags are flying, then there is a parade. We want to show that if it's July 4th, then we have fireworks. So how can we put these three statements in order? How can we arrange them to make an argument that if it's the 4th of July, then we have fireworks? What would we say first? What do you think? Okay. Okay, so we're going to put number 2 first. 2. If it's July 4th, then flags are, this should be then flags are flying. And then 3, if flags are flying, then there's a parade. Then if there's a parade, we have fireworks. So what we did was look for how we can link these together so that the end of one leads to the beginning of the other. So we said, if it's the 4th of July, then flags are flying. That links to this one. If flags are flying, then there's a parade. And that links around to this one. If there is a parade, then we have fireworks. And our argument, our what we end up with is the start of our very first one. If it is the 4th of July, and the end of our very last one, then we have fireworks. So we made an argument that if it's the 4th of July, then we have fireworks. So we put these statements together in a chain that shows that this is the case. Questions on this? And we're just putting them together, and this is kind of what we did, again, what we did with our college trip project. If I want to go to a meeting on Monday, I have to fly to Arizona. If I fly to Arizona, then I have to fly to whatever it was, Coastal Carolina on Tuesday. If I fly to Coastal Carolina on Tuesday, then I go to the meeting on Wednesday. And we're putting those arguments together to make our schedule. That's what we did for our college trip project. What we're using Just so if you see this term in the book, when we're putting the logical chains together like this, it's called the if-then transitive property. And what that means is if we know, if we're given if A then B, and if B then C, we know if A then C. So if we can link these together, we know that if the first thing is true, then the last thing is true. So if you see in the book that talks about the if-then transitive property, all it's talking about is taking these arguments and linking them together one after the other so you can get from the first thing to the last thing. That's really all it's talking about. Any questions? All right. Let me